Okay, shall we get started? Yeah, so today's lecture topic, I want to focus on fault tolerance in general and blockchain as one particular hot topic instantiation of that general principle. So, so this is actually a so these slides are based on a number of existing lectures in this space. Redundancy and fault tolerance is a very old topic in distributed systems and decentralized and fault tolerant systems. And so first I'm going to provide a brief overview of some of the basic concepts of fault tolerance and redundancy, how to keep data consistent and available despite failures, and then despite even malicious failures. And then that'll get us into topics, into a slightly more, we've already touched on blockchain and Bitcoin and stuff like that a few times already in various degrees, but we'll take a slightly deeper look, but still kind of high level summary picture of how Bitcoin and blockchains work, and also smart contracts if we have time. Okay. So redundancy, why do you have redundancy in general? Why do we have two of many different things? So that if one breaks, your pants don't fall down. Whatever. And this applies in many ways throughout our lives and throughout systems we build. And if you want to rely, our trains have many braking systems, so that if one fails or isn't working well, the train can still stop. And anything that you really want to rely on, hopefully you're designing it for redundancy, for the presumption that some part of it will probably fail at some point, and it had better not be disastrous if it does fail. And that's the whole concept of redundancy in computer science. And there's many different aspects, many different approaches to redundancy, many different classes of algorithms that in different ways come down to redundancy. Things like coding. How many of you have studied information coding in a communications context? So many information codes are built with redundancy. So you're transmitting bits across the air. You encode them in such a way that you add more bits, but any small number of them, of those bits, can be flipped or corrupted, and then you get a hope, depending on what coding technique you use, you get a guarantee that you can at least detect that something has gone wrong, and sometimes you can even correct the bit flips for some number of bit flips. So information coding is one very basic, common way to achieve redundancy, and especially in transmissions. Then similarly, data replication. You just take blocks of data and put multiple copies of the blocks, say, on different disks, on different cloud systems, on different computers. So coding and data replication tend to apply for storage and communication of data, but then computations, CPUs can fail too, and computation can fail. Computation can produce the wrong results, and so code can have bugs in it. So in mission-critical systems, for aerospace often, or for really mission-critical systems, sometimes there's been the practice called N-way programming or N-modular programming, where you have 3 different development teams take the same specification and create 3 different software, hardware boxes implementing what's supposed to be exactly the same thing, and then you install them all on the same space shuttle or whatever, and they all check each other, and if one ever disagrees with the other two, you take the majority, whatever the 2 say rather than whatever the 1 say, and hope that that's actually the right answer. Now, there's no fundamental guarantee that, the majority, what the majority says is the right answer, but hopefully it's more likely than the other case, right? And then Things like software replication. If we're worried about just CPU failures due to crashes or bit flips due to cosmic rays, producing wrong answers on one machine, you can have a bunch of machines running the same software, but checking each other's results to make sure you got the same thing. So these are all just different examples of different, in a large space of redundancy, right? So I mentioned first redundancy through information coding. This is used in multiple ways. I mentioned redundancy in communication, transmitting bits over a wire that tends to flip bits fairly often. This is any wireless or physical wire transmission protocol tends to require coding of some kind because we like to push information through our wires and through our airwaves as quickly as we possibly can, which means we have an incentive to turn up the bit rate, but then the higher bit rate we get for a given amount of energy and a given technology, that tends to increase the error rate, the amount of bit flips we see, and so we kind of want to use transmission channels that are fairly lossy, that flip bits fairly often, because that's a way we can get maximized performance out of them. But then we need to recover from those bit flips, those occasional bit flips. And this is what things like forward error correction can handle by correcting some number of bits that get flipped. And then as a backup, things like cyclic redundancy checks or cryptographic MACs, which we've talked about, that can ensure with high probability that a transmission error is detected. It can't correct it, but then we know that we should retransmit that packet or something, right? But then memory system, practically any hardware, physical system that involves storing information is going to have to deal with redundancy. DRAM can, bits stored in a DRAM can get flipped because of cosmic rays or just heat or, random physical effects. This happens all the time. And for this reason, a lot of DRAM comes with ECC, error correcting codes that ensure that occasional bit flips can be corrected without crashing the whole machine, right? And so those are several examples of redundancy through coding. Looking at replication, I mentioned this is common in disk systems, especially there's this very common technique called RAID, redundant array of inexpensive disks, where you. So this was a very important invention from many years ago. That comes in quite a few flavors, but the idea is because disks, traditional mechanical disks were always a fairly common source of failure. Disks would crash, they would get corrupted, because they were such a common source of failure, and we don't want to lose the data on them. RAID and other forms of replicated storage were developed to ensure that we can tolerate the failure of any one or sometimes multiple disks. There's other courses you can take that go deeper in this concept, but just to review a couple of the basic approaches. RAID 1 is what we call mirroring. There's multiple RAID levels, which are really just names for different schemes. RAID 1 is just mirroring. You have two disks with two identical copies of the same data. Anytime you write a sector, you write the same thing to both disks, and then when you read something, you read it from either disk, all of those sectors are hopefully CRC checked, so you'll, with high probability, know if it got corrupted. So if you try to read the sector off one disk and it got corrupted, then the CRC will fail, and you should go try to read the same sector off the other disk. And if one disk fails completely, you just throw it out buy another disk and copy it over again. So obviously this approach can tolerate one failure, right? If you want to tolerate multiple failures, well, you could add more disks. You could mirror across 3 disks instead of 2. That would, in principle, allow you to tolerate 2 failures. But then you've multiplied the cost, the disk cost by 3 instead of 2 for the amount of storage you're getting, right? And so this high cost led to the development of other forms of RAID, some of which are more efficient. For example, RAID 5, where you have some number of disks and you stripe the data, you divide the data so that you have 5 disks to providing the amount of storage of 4 disks, and then you basically you divide each data block into 4 pieces, split those pieces over the first 4 disks, and then add a parity block on the 5th disk. And that way you can still tolerate 1 disk failure. Any one of those disks can fail, and as long as only one fails, then you can recover it from all of the others. And then you only have to pay a 5/4 storage penalty rather than a 2x or 3x penalty to get that redundancy. So that's nicer from a cost perspective, but then there's the trade-off that, well, you can only tolerate 1 failure in a larger set of disks at a time, and many companies have observed that multiple disk failures in a short period are not necessarily that rare, especially when we're looking at modern data centers where you have gazillions of disks in one data center, and some of them are always failing all the time, right? So anyway, storage replication is a deep and interesting topic. There's a lot of different algorithms for that. This is just a sketch of a couple of the standard ones. And so in general, this is all from the observation that we can't deny that things will fail. In the normal case, the code, the computer, somebody else's code, some part of the environment, the power, lightning strikes. Things get flooded, all kinds of things can happen. Back in 2012, some research group from a company called Backblaze noted that using a RAID 6, a reasonably state-of-the-art mirroring not a replication scheme had around 20,000 drives with 40 petabytes of capacity, but they were observing about in these kind of systems fully loaded, they were experience about 60 drive failures per month. And so this is 2 per day that somebody's got to go replace. And if this keeps happening, then sooner or later the probability gets reasonably high that 2 of those disks in one array might fail, making just simple RAID 5 inadequate. For example, you will lose data before too long. And so so it's an important probability calculation typically with redundancy. You have to be aware, how often do failures occur? What's the probability of 2 or 3 or k failures in a short period of time? Say in the case of RAID, what's the probability of multiple failures in the time after the first failure has occurred, but before the system has recovered and re-replicated the contents to a new backup disk, right? So we won't get into all of the details of that, but but just to map out the, we're just trying to map out the area in general and the general concepts and definitions. So one just terminology definition. We have to understand the somewhat subtle differences between different terms and concepts. So when we use the term fault, that usually refers to an underlying, bad thing that happens that can cause a failure. A defect, such as a software bug, that's a fault. A piece of hardware that's gone bad, that's got fried, that is bit flipped or something, or operation, a user error, a user entered the wrong thing, caused a fault. Or the environment, the power grid failed, caused a power failure fault. That's a fault. But a failure is the potential outcome of the fault, the result it causes in the operation of the system. That does if there's a power failure that takes the system, that takes your system offline, so users can't use it, then the power failure is the fault, but the system being online because of that is the failure, right? So kind of subtle definition. One is the cause and one is the result. And of course, if you look at it, there in real systems, there are often many different types of faults. Of course, you might, ideally you have hardware and software that's working perfectly. You might have hardware or software that's most of the time working fine, but it has a subtle defect somewhere, a latent defect that you haven't actually triggered yet, but you might hit at some point, like, a bad bit in the RAM or disk that you just haven't actually used yet. So that's a defective system, but it's not necessarily actually failed yet. There's a fault where maybe the actual bit flip has occurred, but then and then that can further cause things like errors and system malfunctions and stuff. So without trying to get into all the technical details of these many different terms, in general, the fault tolerance is the general term for the goal of designing systems so that they tolerate faults, so that they can allow bits to be flipped or software bugs or a hardware component such as a disk to be fried or to fail, and nevertheless not cause a system failure. So the RAID system as a whole will hopefully keep your data alive and remain available even though one of the disks got fried, and then it alerts you have to take the old disk out, replace it. But if the redundancy system is working as it should, it will be fault tolerant in that the system will keep working. The application will still be able to read and write disks, write the disk, the RAID array, still be able to get data off of it, the correct data off of it. That's what's meant by the system is tolerating fault. It's successfully tolerating faults. It's fault tolerant, right? So now I briefly mentioned the N-way programming. So as a technique for tolerating software faults. So obviously, we need a different technique for tolerating faults in software than faults in just tolerating faults in simple storage, information storage technology. And this is where things like N-way or N-version programming comes in, which, like I mentioned, is used in flight, super safety critical things like aircraft and aerospace systems. And often n equals 3. Very often you want to program those in 3 different versions that all check each other. Now, why not 2? In fact, two versions could be possible. You could create a two-version programming system, and that might be useful in some scenarios. When would it and wouldn't it be useful? Just two-way programming. Obviously, it would be cheaper, right? Well, when might that be useful? Any ideas? So it depends on the needs. So do you have a version in the French language of the English term? There's an English language proverb: someone who has one watch or three knows the time, but someone with two watches is never sure, right? So if you have two redundant systems, you can and they produce different outputs. How do you know which one is correct, right? So you then don't don't have a basis to immediately continue, but you do have a basis for detecting a fault, right? So in some cases, when it's really critical that you be able to detect when something has gone wrong, like when that's all you need, when it's safe to just detect, to be aware that something has gone wrong and stop relying on that system, or it lights up the fault indicator and you say, okay, I can stop relying on it, avoid using that, then maybe just two-way redundancy might be okay, right? But if you're in an airplane, in a space shuttle or something, and we're talking about the control computer that has to be running all the time, if it stops working, if you stop being able to get useful output from it, you're dead probably. Then that's where two-version programming is probably not what you want. Where you really want certainty. You want immediate certainty of a way forward to be able to immediately resolve which, at least immediately make a decision of which answer we think is more likely to correct. Yeah, you had a question, right?
Oh,
yeah.
It was just so in the case that we actually have like three watches, in that case, what if we have like three different values?
Yeah, that's a good question. In the case of three watches, and that can, in principle, happen, with three-way programming too. So. Three-way programming or five-way programming, any way programming for any n is not an absolute guarantee that you will be able to tolerate those faults. So the three could disagree with each other, meaning you don't know which of the three are good, if any, or two of them could agree and one disagrees, but the two are both wrong. The two that agree are both wrong because the software teams that built them, basically did the same bug or misinterpreted the spec in the same way. And this can happen. This can happen too, unfortunately. It's hopefully less likely, but it can happen for sure. So, yeah. Yeah. Exactly. So we're relying on a typically fairly subjective analysis of a probability space that's ultimately unknown, especially when we're talking about software bugs. We really don't know the probability of this or that or the other specific type of software bug. There are important good engineering studies that are there's people, an important interesting research topic is studying from historical bug reports and things. What are the probabilities and commonalities of different types of software bugs? How often do they create vulnerabilities? How often are they, and people have studied the effectiveness of n-way programming, in this regard, and observed that there are classes of bugs where it's unfortunately fairly common that multiple people independently come up with the same bug or misinterpret the spec in the same way. Fortunately, that's not all bugs, and probably not most bugs, but there are bugs that, classes of bugs for which, n-way programming is a very, imperfect, limited solution. So, yeah. So, yeah. So it's ultimately about manipulating a probability space, trying to, reduce the probabilities of failure, even though we can never eliminate them. Yep. So, yeah. In general, there's a very rich engineering literature and practice on different approaches to fault tolerance in systems. You have to consider both detection and response. In some cases, you really only care about detection, and you can shut off or retransmit or recover in some way. Other cases, you really need to be able to recover immediately, and this is what a large class of algorithms in system design, redundant systems, are for. An interesting study is a classic system called the tandem nonstop computer. Now, this is decades ago now, but this company was in operation for quite a while. They developed both an operating system and a CPU, a hardware architecture that would where everything was replicated. They had 2 CPUs, 2 RAMs, 2 sets of disks. Everything about this system was replicated 2 ways, and the CPUs would be in sync, cycles for cycle. Each CPU would be executing the same instructions, cycle for cycle, independently, and then in order to try to tolerate any fault in the software or hardware system. Well, not any fault, right? Because what did I just say? If you have, this is a 2-watch system rather than a 3-watch system, right? So what's the deal here? Well, what Tandem was actually doing was being able to tolerate any detectable fault or detected fault, right? So they were relying on the fact that the most common failures, especially in the hardware world, tend to be detectable things like bit flips in a memory where you can detect a bit flip using ECC or CRCs. Processors have a lot of detection capabilities. Often when there's a bit flip or something goes wrong at a processor level, that very often causes an immediate crash of some kind. Or a machine check. How many of you have seen a machine check exception kill your machine? I don't. So many operating systems. I don't know if Windows still reports machine check exceptions with that name. It used to. Many operating systems increasingly have become so obsessed with user friendliness that they don't tell you what went wrong anymore. They just say, like Mac, something went wrong with your computer, rebooting, or but buried way down there somewhere, if you care to check the logs, you might sometimes find out that those are machine check. Some of those might be machine check exceptions, which is the processor detecting that there was a bad bit flip somewhere, and so basically Tandem was relying on the fact that many types of faults, the most common types of faults, often tend to be quickly detectable, and so they built the system so that when a fault is detected, it would quickly shut off that side or restart that side and continue running the other one. The basic purpose being to be able to continue running in the presence of a fault with no stopping, no need to, delay to reboot, a system or replace it with a different machine. Literally non-stop was the goal. Yeah.
And one of these machines, so one of the virtual machines, right? Gets shut down and afterwards gets restarted. It it starts from the same point where the first machine is running.
Yeah, so that was one of the very interesting engineering challenges of the nonstop. You know, if one side gets shut down and then you have to restart it, well, they needed to reinitialize, you know, kind of bring up the DRAM state of one side with respect to the other, right? And it, you know, has to catch up to the, you know, cycle by cycle parity with the other machine and then continue from there. And I'm not sure in the details. So, you know, there's ways to do this with virtual machines. This was not a virtual machine system. This was way before VMware and, you know, these kinds of approaches. Of course, VMware and virtual machines can do this kind of thing too. And there are other standard software-based approaches to, you know, bring up a new virtual machine into synchrony with another virtual machine, or also to migrate virtual machines. One of the standard practices for you want to migrate a virtual machine from one physical machine to another. But you don't want to shut it down for the entire process of copying all the data over. You've got to, you know, transfer the state of the old virtual machine to the new one while the old one is still computing and changing its state. But then, you know, you need to try to make a copy, understand that some of that state is going to continue getting changed, and then you got to go copy that too, and, you know, kind of do an iterative process to catch up. Until you're close enough that maybe, at least in virtual machines, you always eventually have to kind of get close to having all the state synchronized and then stop briefly to do the last little bit of synchronization to get them in a perfectly synchronized point, and then you start again. Now, I'm not sure if Tandem did even a brief stop or if they had some really, really careful dance that allowed them to synchronize, you know, kind of perfectly, like, you know, copy the DRAM in parallel with, you know, to get a recovered side up with respect to the other one. But in general, that's an interesting challenge. Recovery is always an interesting, non-trivial challenge. Right? Yeah, so good question. So yeah, so these are, so this is just intended to be an overview of several different classic approaches to redundancy, some of which are still in very common use. The tandem computer is not, you know, that's kind of history now, but it's that approach in general, like I alluded to, has lived on in the uses of virtual machines and other redundant systems. In general, one of the common objectives we want from fault-tolerant systems is high availability. What we mean here is the system is there and responsive when you need it to be. It's available almost all the time. It guarantees a response even when some things go wrong somewhere. And in distributed systems, we often talk about availability in the face of network failures, network partitions, where, you know, some part of the distributed system is disconnected from the network, unable to communicate or crashed or something. And so let's look at an example of high availability in a distributed context. Actually, I can't remember what exactly that animation was supposed to be illustrating, so I'll skip that. But it was, right. So if you have a distributed system with state in multiple locations, yeah, I think we're missing some part of that animation, sorry. Not sure what happened to it. But those two systems can't communicate with each other. Then obviously they can't, there's no way they can remain available, but also consistent with each other. Because if they're both serving transactions or allowing their serving requests, changing their states, they're going to be doing so independently without knowledge of each other. It's, you know, just the fundamental fact of partitioning, right? And so a very important important fundamental question is what happens then in the case of network partition, and how do we design our systems to behave in the face of network partitions, right? Yeah, so and many network people and companies have observed that, well, you know, the internet is supposed to make network partitions extremely rare, but in various contexts, it's, you know, just like multi-disk failures in a RAID array, network partitions are not that uncommon on the internet either, for various reasons, in various contexts. So with this in mind, you know, the fact that partitions happen, this brings us to one of the very fundamental theorems that gets used a lot and referred to a lot, for better or worse, in thinking about distributed systems and availability and fault tolerance, the CAP theorem. So what is the CAP theorem? You know, I won't get into the formal technical definition, but basically it's an impossibility result that basically says, you know, in the general case, you know, in networked system, distributed systems with failure, with partitions, you can get only two of these three things: consistency, availability, and partition tolerance. You know, you pick two, and you'll have to give up the third, right? So, for example, on the internet, you know, since the internet clearly is partitionable, you know, we observe empirically that partitions do occur on the internet. You know, on the internet, we don't get partition tolerance. We kind of have to give up that. But, you know, if we're willing to give that up, we can get consistency and availability. You know, but only in systems, you know, that aren't the internet. You know, in other words, right? If we are on the internet and you know, and partitions can occur, then we're going to have to give up either consistency or availability in the general case, right? So, yeah. So, yeah. Consistency is also a complex subject with a lot of different definitions. There's different forms of consistency. Strong consistency, for example, is basically multiple parties, when multiple parties try to access a common you know, logical memory cell or logical state. Do they all if you have strong consistency, then you have a guarantee that anybody who reads the state after somebody else in the system wrote it will see that most recent state, the most recently written state by anyone else in the system, right? So effects propagate, right? But you can see just kind of intuitively why you fundamentally, you know, if you want to allow a write to happen over here and a read to happen over here of that state, but there might be a partition in the middle, well, there's no way for the state, you know, the fact that this write happened to propagate over here so that this reader will be aware of that. You know, so that's you know, kind of a fundamental, just a simple intuitive illustration of why you at least can't get strong consistency with both availability and in the presence of partitions, right? And so strong consistency, like I said, is only one of many consistency models. There's linearizability, which is a very slightly weaker, but it's also, you can't get linearizability either together with availability and partition tolerance. You also There are even weaker schemes such as eventual consistency, that can, under the right circumstances, get you availability, partition tolerance, and this weaker consistency scheme. But, so here we're really talking about, the CAP theorem really talks about strong consistency, right? So let's look at the choice if you choose to give up strong consistency. That's one of the common trade-offs that we make. If we're willing to live with weaker consistency, such as eventual consistency or causal consistency, there's various weaker consistency models that then we're saying that, okay, we have these two or more nodes in different parts of the systems that might be partitioned. The availability property means that we want all of them to be responsive. If clients are making requests to this one on this side of the partition and clients are making requests to that one on that side of the partition, we want them, both of those nodes to be responding independently. That means, we want availability, but they have to, but because we also want partition tolerance in this example, that means that they have to be able to respond even though they are not able to coordinate with each other, right? And so that's why we can't get consistency in general in that model. So, but again, this is a useful model in quite a few situations, and it's used often. Like the domain name system is actually a fairly weakly consistent system in that, the DNS lookup results you're getting from, you cache them for a while, and if they change, well, you're not actually going to know that they changed until your current cached version times out, and and you can get copies of them from various nodes around the internet. It's a really very weakly consistent scheme. It's also partly because of that and partly because of other flaws. It's also a not very secure scheme. How many of you have heard of DNS poisoning attacks? Yeah. So this is a nice little hacker technique hackers do to. They poison different levels of the DNS cache hierarchy with fake DNS answers in hopes of sending your web browser or your application to the wrong IP address, to the hacker's IP address instead of the right one, and being able to present you a fake web page and harvest your credentials or stuff like that, right? So DNS is very weakly consistent. But often things like, in the case of Amazon shopping and other shopping carts, often, when you're just putting things in a shopping cart and viewing the shopping cart, customers, so Amazon and other online retailers have observed that customers really care about seeing an answer, quickly. But maybe are a little bit more tolerant if the answer is not necessary. It might be possible in some cases to see a slightly stale answer from this query on this machine versus this other query on this machine. So, in fact, many of you, you might have experienced one form of weak, very eventual consistency with Amazon or other retailers. If you have, get on Amazon from a machine different from your usual machine, you're not logged in, so you see a blank shopping cart, but then you log in, and then suddenly you see, some other stuff appear in the shopping cart, and they often allow you to add stuff to the shopping cart in your, not logged in context, and then you log in, and it merges that with the shopping cart context from your account that you were logged in under in another context. And so in many situations like these, it's fairly applications tend to be fairly tolerant of not seeing the very latest thing necessarily, just something reasonable and reasonably recent. And so so this can be a good trade-off when it's important for high availability and low latency with respect to a particular customer or particular user in a particular location. You want to send the user to the nearest data center to get a fast response, but it doesn't need to be the absolute most up-to-date. Yeah, but obviously there are applications for which that isn't such a good choice, and so the CP choice, the choice where we insist on strong consistency and partition tolerance, but as a cost of achieving that, we're willing to give up availability, some amount, right? So in this case, we're saying that in that event where we've got these two parts of the system and they're network partitioned, we're going to say that at least one side of those, maybe both, but at least one of those is not going to be available, is not going to be able to respond successfully to requests until the partition is healed or somebody manually resets the system or something, right? So this fundamentally, achieving strong consistency in a distributing system fundamentally needs coordination. This can increase latency. It requires these nodes to communicate. If that communication is costly because it's across the world, then that can increase the latency because of this coordination. And it certainly can compromise the availability, right? But strong consistency as well as linearizability, are convenient models in that they guarantee many intuitive properties like atomicity. If you did something to a datum item over here and then you observe it over here, you don't see things going backward in time. Whereas in other consistency models you can see what looks like time travel effects. Like, I did something over here, and then I saw an earlier version of the state from this other context. Okay, so those are the basic ideas. Now, of course, so I just covered the AP and CP choices. CA, consistency and availability, is also a choice, but that's basically fundamentally only applicable in a context in which I can guarantee that there's going to be no network partitions. Can you think of any examples of that? Like where we might have a CA choice example? Yeah. Yeah. So kind of a local system, or the tandem nonstop computer that I mentioned earlier. Of course, that has an internal interconnect between the two redundant things, or in a tightly connected thing where any context where if the network fails, if the kind of by design, if the communication links fail between these, then you say it's all over. That's a critical failure that we're not even going to try to deal with. We're going to just design the network so it's redundant, and the network itself is going to be redundant and high availability enough that we just assume that the network never fails and never partitions. And if it does, it's all over. We throw our hands up, declare we're dead, and that's a hard failure then, right? So that would be the CA approach, and it's effectively often the case when you're dealing with local area systems where you just design in an assumption that we're going to make it so astronomically improbable that the network fabric fails that we're going to treat that as a hard failure. Okay, so let's take a quick break, like a 10-minute break, come back at 5:15, and we'll continue with consensus and blockchains.